They told us the universe began with a bang, an explosion so vast it birthed time, space, and everything we know. But what if this story is wrong? What if the Big Bang wasn't the beginning of the universe, but the aftermath of something far stranger? Some scientists now argue we're not just in the universe, we're trapped inside the belly of a cosmic beast, a black hole so immense it swallowed a higher dimensional reality and spit out the one we live in. If that's true, what does it mean for us? For reality? And if we're inside a black hole, does that mean everything we've ever known is false? The intrigue of black holes. Black holes are among the strangest things in the universe. These invisible regions of space aren't just fascinating for their extreme gravity, they challenge what we know about reality itself. The story of how black holes went from wild ideas to key pieces of modern science is filled with twists and turns that are just as interesting as the phenomena themselves. It's not just their pull on stars and planets that makes them significant. It's their pull on the human imagination and our understanding of the cosmos. The idea of black holes can be traced back to the 18th century, when John Michell, a British clergyman and scientist, speculated about dark stars. He proposed that some stars could be so dense their gravity would trap even light. Of course, Michell didn't call them black holes. He had no way of proving his theory. Yet his work laid the groundwork for future scientists. At the time, Michell's ideas were more like thought experiments. It would take nearly 200 years for these concepts to resurface as serious science. Fast forward to the early 20th century. Albert Einstein's theory of general relativity changed everything we thought we knew about gravity. Instead of thinking of gravity as a force, Einstein described it as the bending of space-time. Heavy objects like stars warp the space around them, and smaller objects follow these curves. This shift in understanding opened the door to the possibility of black holes. Einstein himself wasn't a fan of the idea. He found it hard to believe that nature would allow such extreme structures to exist. But mathematics doesn't care about preferences. When Karl Schwarzschild solved Einstein's equations in 1916, he found something astonishing. Under certain conditions, a star could collapse into a point so dense it would create a gravitational sinkhole, now known as a black hole. Schwarzschild's discovery was monumental, but it was also overshadowed by World War I. He worked on these equations while serving in the German army, often under dangerous conditions. Despite the odds, his findings gave scientists a new way to think about the universe. Schwarzschild's work described not only the existence of black holes, but also their boundaries, now called event horizons. This is the point of no return. Anything that crosses it, even light, cannot escape. Even with Schwarzschild's findings, black holes remained a curiosity. Many scientists doubted they could exist in the real universe. Einstein continued to push back against the idea, calling them gross misinterpretations of his work. It wasn't until decades later, when astronomers started finding evidence of strange objects in the cosmos, that black holes began to look real. The discovery of Cygnus X1 in the 1960s changed everything. Here was a binary system where one star seemed to orbit nothing. That nothing was eventually identified as a black hole, the first of its kind to be widely accepted by the scientific community. What makes black holes even more fascinating is how they challenge our understanding of space and time. Near a black hole, time slows down. This isn't just theoretical, it's been observed. In regions with extreme gravity, clocks tick more slowly. If you were to hover near a black hole and look back at Earth, time would seem to move faster here than it does there. This warping of time and space isn't just a curiosity, it's part of why some scientists think black holes might hold the answers to some of the universe's biggest mysteries. However, black holes aren't only mysteries to scientists. Art and literature have also been captivated by them. Poets and writers have been conjuring such cosmic holes for a long time, even before scientists could provide proof of their existence. The cosmos is crashing down on itself, according to Edgar Allan Poe's poem Eureka. Although his vision does not align with scientific accuracy, it does align with the contemporary idea of a singularity. Inspired by Einstein's work, surrealist painters such as Salvador Dali incorporated concepts of endless. In the 20th century, black holes became symbols of both fear and fascination in popular culture. The term black hole itself wasn't coined until 1967 by physicist John Archibald Wheeler. Before that, they were referred to as frozen stars or dark stars. The new name stuck, partly because it captured the sense of mystery surrounding these objects. Movies like Disney's The Black Hole and later films such as Interstellar turned these cosmic enigmas into major plot points, blending science with imagination. Yet even as black holes became household terms, the science behind them remained deeply complex and in many ways elusive. Unlike what one might expect, black holes actively seek out and consume anything that gets in their way. They're living, breathing things. A gaseous and debris-filled ring known as an accretion disk is created as matter spirals in the direction of a black hole. When these disks get hot enough, they release intense X-rays that astronomers on Earth are able to detect. Jets, which are energy streams that escape from black holes at almost light speed, are another feature of these objects. The development of galaxies and the distribution of matter in the universe are both affected by these jets, which may span for thousands of light years. The connection between black holes and the larger structure of the cosmos is one of the reasons scientists take them so seriously. Supermassive black holes, like the one at the center of our galaxy, Sagittarius A star, play a critical role in shaping their environments. These cosmic giants can weigh millions or even billions of times more than our Sun, yet they occupy a space no larger than our solar system. Their gravitational pull holds entire galaxies together. Without them, it's unclear if galaxies, and by extension life as we know it, could exist. Not all cultures have seen black holes or similar concepts as symbols of destruction. In Hindu cosmology, there's the idea of endless cycles of creation and destruction. Some interpretations of these myths align surprisingly well with modern scientific theories. The dance of Shiva, representing creation and destruction, has parallels to how black holes consume and redistribute matter. Indigenous myths too speak of devourers of light, or cosmic voids, suggesting that humanity has long grappled with the idea of things beyond comprehension. Black holes are fascinating for reasons beyond their cultural connotations alone. Furthermore, they test the boundaries of what we can learn from science. At the very core of a black hole, where density is limitless, lies one of the greatest mysteries in the universe: the singularity. Our current understanding of the principles of physics fails us in this case. There, the concepts of space and time become meaningless. If we could only decipher singularities, say some physicists, we could learn how the cosmos came to be. The Big Bang may have been a singularity in and of itself, marking the beginning of the universe as we know it from an extremely dense point. The interconnections between black holes and other cosmic events are much more intriguing. The most brilliant lights in the cosmos, known as quasars, are fueled by supermassive black holes. Their discovery shed light on how these things operate. Black holes power quasars, which produce more energy than whole galaxies. Black holes continue to captivate scientists and the general public, due in part to their paradoxical character as both makers and destroyers. Modern tools have given us an even closer look at black holes. The Event Horizon Telescope, a global network of observatories, captured the first ever image of a black hole in 2019. This image of the supermassive black hole in galaxy M87 wasn't just a scientific triumph, it was a cultural milestone. For the first time, we could see the shadow of a black hole, surrounded by the bright ring of its accretion disk. This confirmed many predictions made by general relativity, but it also raised new questions. What lies beyond the shadow? Could these regions hold clues about the universe's hidden dimensions? The idea that our universe might be inside a black hole isn't as far-fetched as it sounds. Some scientists propose that black holes in higher dimensional space could create universes within them. This theory ties into the holographic principle, which suggests that everything we experience in 3 dimensions might be a projection from a 2-dimensional surface. In this view, black holes aren't just cosmic oddities, they're gateways to understanding the fundamental nature of reality. This connection between black holes and the universe's structure has deepened with the study of gravitational waves. These ripples in space-time, first detected in 2015, are often caused by collisions between black holes. Observing these waves allows scientists to listen to the universe in a completely new way. Each detection provides more evidence for the strange and interconnected nature of black holes and the cosmos. While we still don't have all the answers, black holes are more than just regions of space where gravity reigns supreme. They're key to understanding everything from the birth of galaxies to the potential end of the universe. Whether they hold the secrets to alternate realities or simply show us the limits of our current understanding, they remain among the most mysterious and captivating objects in the cosmos. Basics of black hole theory. Albert Einstein's theory of general relativity forever changed how we think about space, time, and gravity. Before this theory, gravity was thought to be a force between 2 objects, like the Earth and the Moon. Einstein's idea was different. He proposed that gravity isn't a force at all, but the bending of spacetime caused by the presence of mass. Heavy objects, like stars or planets, create curves in spacetime, and other objects move along these curves. It's like placing a heavy ball on a stretched rubber sheet. The ball creates a dip, and smaller objects roll toward it. This new way of understanding gravity wasn't just theoretical. It explained many things about how the universe works, and one of its most fascinating predictions was the existence of black holes. Black holes weren't immediately accepted as real objects. When Einstein published his equations in 1915, even he doubted they could exist. The idea seemed too strange, places where gravity is so strong that nothing, not even light, could escape. But Einstein's equations didn't lie. In 1916, Karl Schwarzschild solved these equations for the first time under extreme conditions. His solution showed that if a star were massive enough and collapsed under its own gravity, it could form a point of infinite density, a singularity. Around this singularity would be an invisible boundary, later called the event horizon. Anything crossing this boundary would be lost forever, unable to return. Schwarzschild's work was groundbreaking, but it was overshadowed by the chaos of World War I. He worked on his equations while serving in the German army, and he didn't live to see their full impact. Still, his discovery laid the foundation for what we now know as black holes. The event horizon is a key feature of black holes. It's not a physical surface like the ground we walk on. Instead, it's a mathematical boundary. If you get too close, the escape velocity, the speed needed to break free from gravity, becomes greater than the speed of light. Since nothing can travel faster than light, nothing can escape once it crosses this boundary. Inside the event horizon, the rules of physics as we know them stop making sense. Time and space are so warped that they become almost meaningless. At the center of the black hole lies the singularity, where density becomes infinite, and the curvature of spacetime becomes infinite as well. The singularity is hidden from the outside world by the event horizon, which is why we can't observe it directly. Some scientists even question whether singularities truly exist, or if they are simply a sign that our understanding of physics is incomplete. Not all black holes are the same. They come in different sizes and types. Stellar black holes form when massive stars collapse at the end of their life cycles. These black holes are typically a few times the mass of our Sun. Then there are supermassive black holes, which are millions or even billions of times more massive than the Sun. These giants sit at the centers of most galaxies, including our own Milky Way, where a supermassive black hole called Sagittarius A star resides. There are also intermediate black holes, which are smaller than supermassive ones, but larger than stellar black holes. These are harder to find, and are thought to form through the merging of smaller black holes. Lastly, there are primordial black holes, which, if they exist, were formed in the early universe. These tiny black holes might even help explain dark matter, the mysterious substance that makes up most of the universe's mass. The characteristics of a black hole can also affect its behavior. As it spins, a Kerr black hole, a type of rotating black hole, pulls space-time around with it. Experiments such as Gravity Probe B validated this phenomenon, which is known as frame dragging. A further variety is the electric-charged black hole, also known as the Reisner-Nordstrom black hole. Although they might theoretically exist, charged black holes are highly improbable to occur in the real world due to the electrical neutrality of most space objects. Emissions of energy are one of the most fascinating features of black holes. Black holes aren't totally opaque, even if nothing can evade their event horizon. A gaseous and dusty ring known as an accretion disk is created as material falls in the direction of a black hole. As the disk's contents reach temperatures in the millions of degrees, they release radiation that our planet's atmosphere may pick up, including X-rays. Additionally, some black holes release extremely strong energy jets that launch particles outward at almost the speed of light. Stars and galaxies are shaped by these jets, which may be thousands of light-years long. Time seems to stand still when one is close to a black hole, in contrast to further away. This phenomenon, known as time dilation, is not limited to theory. In our trials here on Earth, we have seen results that are quite comparable. A good example of this is the fact that the rate of ticking of a clock decreases as the gravitational field strength increases. This effect is at its strongest in the vicinity of a black hole. Time would seem to stand still for you as you hovered just outside the event horizon, allowing you to observe the cosmos accelerate around you. The study of black holes has also helped us understand other cosmic phenomena. For example, quasars, some of the brightest objects in the universe, are powered by supermassive black holes at the centers of galaxies. These black holes consume massive amounts of gas and dust, and the energy released in the process can outshine entire galaxies. Quasars are a striking example of how black holes, often thought of as destroyers, can also be sources of immense energy. Black holes also play a role in the expansion of the universe. Observations of gravitational waves, ripples in spacetime caused by the collision of massive objects, have provided direct evidence of black hole mergers. These waves were first detected in 2015 by the LIGO Observatory and have since become a valuable tool for studying black holes. Each detection not only confirms Einstein's predictions, but also helps scientists learn more about the universe's most extreme events. Hawking radiation, a concept proposed by Stephen Hawking, adds another layer of complexity to black holes. According to quantum mechanics, black holes aren't completely black. They slowly lose energy through a process that involves virtual particles forming near the event horizon. Over time, this energy loss causes the black hole to shrink and eventually evaporate. While Hawking radiation has yet to be observed directly, it has profound implications for our understanding of black holes and the laws of physics. Some scientists also speculate that black holes could be connected to other parts of the universe through wormholes, theoretical tunnels that link different points in space-time. These ideas are purely theoretical for now, but they raise intriguing possibilities about the nature of reality and the structure of the cosmos. The holographic principle, another theoretical concept, suggests that everything inside a black hole might be encoded on its event horizon. This idea has led to new ways of thinking about information, entropy, and the universe as a whole. Black holes are not just objects of scientific curiosity, they are essential to understanding the universe. From their formation to their role in shaping galaxies, they challenge our understanding of physics and push the boundaries of what we know about space and time. Whether through their immense gravitational pull, their ability to bend light, or their mysterious singularities, black holes continue to captivate scientists and the public alike. Foundational ideas of the black hole universe. Hypothesis. String theory offers a surprising idea that our universe may have more dimensions than the 3 we know. In this theory, there could be up to 10 or even 11 dimensions, but these extra dimensions are hidden. They are so small and curled up that we don't notice them in our daily lives. They're not like length, width, or height, but exist on a different scale. These hidden dimensions are essential to string theory, and without them, the math doesn't work out. When scientists talk about a universe within a black hole, these extra dimensions are part of the puzzle. In brain cosmology, a model from string theory, the universe we experience is just one part of a larger structure. According to this idea, our universe is a brain floating in a higher dimensional space, often called the bulk. We're like a sheet within this larger space, and other brains could exist around us. Black holes, in this view, might be connections between brains or even gateways to other dimensions. Gravity, for instance, might be weaker than the other fundamental forces because some of it escapes our brain into the bulk. This idea helps explain why gravity feels so weak compared to forces like electromagnetism or the nuclear forces. Scientists think black holes might be higher dimensional objects too. If we could see them from a higher dimensional viewpoint, they might not look the same as they do in 3-dimensional space. In our universe, black holes appear as points of infinite density surrounded by event horizons. But in higher dimensions, they could have much more complex shapes like spheres or other forms, and their properties might change. Some theories suggest black holes in higher dimensions could pinch off pieces of spacetime itself, creating something new, a process that might even lead to the birth of a new universe. M-theory, a more advanced version of string theory, takes these ideas even further. It says that to understand everything in the universe, we need to work with 11 dimensions. This theory unifies all known forces, including gravity, electromagnetism, and the forces that hold atoms together. In M-theory, black holes are not just 3-dimensional points, but could be higher dimensional objects called black brains that extend across multiple dimensions. These black brains could affect not just our universe, but other dimensions or universes at the same time. Some researchers think that the birth of our universe could be the result of a black hole collapse in a higher dimension, with the Big Bang as its aftermath. This brings us to the black hole universe hypothesis, which suggests that conditions inside a black hole could resemble those of a Big Bang. Imagine all the matter and energy inside a black hole, compressed to a point where space and time break down. Some scientists propose that this immense compression could spark the formation of a new universe with its own rules and structure. The event horizon of a black hole might act like a boundary between universes. Just as we can't see beyond the edges of our universe, nothing can escape from beyond the event horizon. It's a boundary in both cases, separating different worlds. Some observations about our own universe might hint at this idea. When scientists study the cosmic microwave background, the faint glow left over from the early universe, they see patterns that are hard to explain. A few scientists think these patterns could be echoes from a black hole's collapse if our universe formed within one. And if we live inside a black hole, it could explain why we can't find an edge to our universe. Just as the event horizon hides what's inside a black hole from view, our universe might have a similar edge that we can't see past. The holographic principle is another important part of this puzzle. It suggests that everything we experience in 3 dimensions is actually encoded on a 2-dimensional surface. This idea first emerged in studies of black holes. Researchers found that the information about what falls into a black hole seems to be stored on its surface, not inside. If this is true, then our reality might be a kind of projection, with everything inside a black hole represented on its outer layer. In this view, black holes aren't just cosmic vacuums. They're information storage devices, encoding details about their parent universes. The strange connection between black holes and the universe goes even further. Some scientists believe that black holes could help explain why the universe is expanding faster. Dark energy, The mysterious force causing this acceleration might come from interactions with something outside our universe. If our universe is inside a black hole, then the outer universe could be pulling on it, causing expansion. This would mean that the accelerated expansion we see is not just a property of our universe, but a result of its connection to a larger structure. This black hole hypothesis connects to the laws of thermodynamics, especially the second law, which states that entropy or disorder always increases. Black holes have entropy too, which depends on the surface area of their event horizon. This finding surprised scientists because it suggests a link between black holes and space-time itself. It also ties into the holographic principle, where the surface area, not volume, holds all the information. If our universe is inside a black hole, its entropy might be stored on a two-dimensional boundary, giving a new perspective on the structure of reality. The concept of time also behaves strangely in a black hole. As objects move closer to the event horizon, time slows down relative to an outside observer. This effect, called time dilation, could provide a clue about why our universe's expansion appears to be accelerating. From within a black hole, time and space could be distorted in ways that make expansion look faster. This idea ties into the black hole universe hypothesis, where the flow of time inside a black hole differs from the flow of time outside it. These ideas don't just apply to black holes in our universe, they extend to black holes in other universes, if they exist. In M-theory and brain cosmology, black holes can influence multiple universes or dimensions. They might act as anchors or nodes, connecting different parts of the multiverse. Some researchers even think that black holes could create baby universes, smaller regions of space-time that branch off from a larger universe. This branching process would mean that black holes are like cosmic seeds, growing new universes within them. Quantum gravity, the effort to unify quantum mechanics with general relativity, also relies on black holes as test cases. Some quantum gravity theories suggest that black holes contain quantum seeds that could grow into new universes under the right conditions. These seeds could carry the initial conditions of a universe, providing a framework for how it might develop. The Planck scale conditions near a black hole's singularity, the area of highest density and smallest scales, could resemble the conditions at the start of our own universe, supporting the hypothesis that black holes create new realities. Even observational clues suggest that something strange is happening on the grandest scales. Dark energy, which makes up most of the universe's energy, might be a kind of force or energy exchange with a parent universe outside the black hole. This exchange would act like a cosmic push, expanding our universe from within. Black hole thermodynamics, which studies the temperature and entropy of black holes, also provides hints. Black hole entropy scales with the area of the event horizon, not its volume, implying that the structure of space-time could be closely tied to black holes. The ideas linking black holes to other universes may sound complex, but they create a fascinating picture of how the universe might work. They suggest that black holes are not just points of infinite gravity, but key elements in a much larger cosmic structure. This view challenges the traditional Big Bang theory as a one-time event, proposing instead that our universe could be one of many created in a multiverse filled with black holes. Multiverse theories and black holes as portals. A universe where the choices you make have the power to shape reality itself. Instead of turning right, you turn left in one. On the other hand, you decide not to have lunch. When these subtle variations are replicated across an infinite number of possible outcomes, the result is a huge multiverse. Though it may sound fantastical, the concept of parallel worlds really originates in quantum physics, which asserts that particles can exist in more than one state simultaneously. Some researchers are now considering the possibility that black holes hold the secret to these parallel universes. One theory suggests that each universe is like a bubble in an infinite foam of universes. Each bubble forms when a new universe pops into existence, often with its own laws of physics and fundamental constants. These universes are completely separate from ours, or are they? Black holes might actually act as bridges between these bubbles, connecting them through their intense gravitational pull. The idea is that black holes could link universes, allowing energy, matter, or even information to travel between them. In this sense, black holes become gateways, connecting what we thought were isolated realms. In another version of the multiverse, known as the brane theory, our universe is just one three-dimensional brane floating in a higher dimensional space called the bulk. Think of it like a piece of paper drifting in a larger space, with other pieces of paper nearby. If black holes exist on these branes, they might create connections between them. These connections would be invisible to us, but they could allow energy or gravity to seep from one brane to another. This might explain why gravity feels so weak in our universe. It's leaking into other branes through black holes. Once something crosses the event horizon, it's gone forever, right? But what if that's not the full story? Some scientists suggest that the singularity inside a black hole could be connected to a white hole in another universe. A white hole would be the opposite of a black hole, expelling matter instead of pulling it in. If this connection exists, it would mean that what falls into a black hole in our universe might emerge in a different form somewhere else. This connection might not be visible from outside the black hole, but it could mean that black holes are more than just cosmic dead ends. They might be points of exchange, where universes interact in ways we can't yet fully understand. Wormholes, often imagined as shortcuts through space, could play a role here too. Some researchers think black holes might stabilize wormholes, creating bridges not just through space, but across different universes. If these wormholes exist, they wouldn't be easy to travel through. The energy needed to keep them open would be immense, possibly drawn from the rotation of the black hole itself. And they might not connect 2 points in our universe, but link different universes all together, forming a network where black holes act as transit hubs between realities. To stabilize a wormhole, scientists believe you would need something called exotic matter, which has negative energy. This exotic matter doesn't exist in our everyday world, but theoretically, it could hold open a wormhole, making a passage through it possible. Some physicists think that at microscopic scales, black holes might contain tiny quantum wormholes that connect to other universes on a quantum level. These tiny wormholes could represent an unseen web that links not just galaxies, but entire universes. If black holes connect universes, it would reshape our idea of reality. Instead of a single closed universe, we might be part of a network where each universe is linked to others, with black holes acting as cosmic doorways. This would mean that our universe is not isolated, but instead part of an intricate web, and black holes play a central role in this system. It also challenges the idea of boundaries. If black holes are portals, there might not be a true edge to our universe. Instead, each black hole could lead to an entirely new realm. Black holes might recycle matter and energy from one universe and send it into another. This would make black holes more than just endpoints. They'd be cosmic recycling centers, breaking down matter in one universe and reshaping it in another. If black holes allow energy to travel between universes, it could also explain some of the mysteries in our own universe, like dark energy, the force pushing everything apart at an increasing rate. Some scientists suggest that this expansion could be influenced by forces from other universes interacting with ours through black holes, subtly nudging everything outward. This idea also plays into the black hole information paradox. In traditional physics, information is never truly lost. But when something falls into a black hole, it seems like the information about it is erased. This puzzles scientists, who wonder if this information somehow travels to another universe instead. If black holes are portals, the information could be preserved, just in a different form, in a different universe. This means that what we see as lost could simply be crossing a threshold we don't yet understand. The laws of quantum mechanics and relativity both come into play here. Quantum entanglement, a phenomenon where particles remain linked even over vast distances, might suggest a hidden connection between black holes in different universes. This could mean that black holes aren't just isolated objects, but part of a vast, interconnected structure. When two black holes merge, they release gravitational waves, ripples in space-time that travel across the universe. Some scientists think these waves might even carry signals from other universes, leaving faint echoes that we could one day detect. If this is true, every black hole merger might reveal more about the structure of the multiverse. There are other clues, too. When scientists study the cosmic microwave background, the faint radiation left from the early universe, they sometimes find patterns that are hard to explain. Some believe these patterns could be traces of interactions with other universes, possibly through black holes. And then there are gamma-ray bursts, intense flashes of energy that seem to come from distant galaxies. These bursts are so powerful that they raise questions about their origins. Some scientists wonder if they might be signals from high-energy events involving black holes in other universes. Even Hawking radiation, the slow release of energy from black holes, might hold clues about other realms. If the radiation patterns from a black hole don't match what we expect, it might suggest that something unusual is happening, like energy leaking from another universe. Observing these differences could provide hints about what lies beyond our universe. All these theories come with big questions. If black holes are indeed portals, what happens to objects that cross the event horizon? Are they destroyed, or do they reassemble in another universe? If black holes connect universes, it challenges the long-held belief that nothing can escape. Some scientists think black holes might be one-way doors, letting matter flow in only one direction. Others wonder if some black holes could allow energy to travel in both directions, forming a bridge that lets energy and maybe even information flow back and forth. The idea of black holes as portals to other universes is not just a fantasy. It's a way of looking at the universe that challenges what we know and invites us to imagine what might lie beyond. If black holes truly are gateways, they might hold the secrets to a multiverse more vast and intricate than anything we've ever dreamed of. Each black hole could be a portal. Each portal a doorway to a reality just as real as our own, yet forever hidden on the other side of the stars. Einstein's field equations might sound abstract, but they're at the core of what we know about black holes. They don't just give us numbers. They lay out how space and time twist, bend, and stretch under extreme gravity. These equations are complicated, 10 interlinked differential equations that connect mass, energy, and the curvature of space-time. When Einstein published them in 1915, he probably didn't envision the future applications, but today they're key to understanding black holes. The complexity of these equations becomes more apparent as scientists apply them to black holes. Under certain conditions, the equations predict that space-time can collapse into a point with infinite density, creating what we know as a black hole. Carl Schwarzschild was the first to solve these equations for a simple black hole, a non-rotating, perfectly spherical one. This solution, known as the Schwarzschild solution, defines the event horizon and predicts how light and matter would behave around it. But real black holes are rarely this simple. They rotate, they interact, and they collide with each other, requiring more complex solutions and, more often than not, computational help. For rotating black holes, the Kerr solution adds another layer. It describes how a black hole's spin distorts space-time, creating a kind of cosmic whirlpool where space itself twists. This effect, known as frame dragging, is so powerful that it warps everything around the black hole, including light. The equations describing this rotation are far too complex to solve by hand, so scientists use computers to run simulations that capture these dynamics in detail. Creating a black hole simulation isn't just a matter of plugging numbers into a computer. Each black hole is broken down into tiny elements, like a grid overlaying spacetime. Scientists calculate the gravitational pull on each point of this grid based on nearby points, updating these positions with each passing fraction of a second. This approach is called numerical relativity, where computers handle the massive calculations needed to keep up with Einstein's equations in real time. One approach, called finite difference, uses the grid to divide the differential equations into smaller, more manageable stages. By tracking the evolution of spacetime at each stage, researchers may piece together a picture of a black hole's actions throughout time. By directing processing resources to key regions, such as the event horizon, adaptive mesh refinement is an additional method. When dealing with complicated phenomena like black holes, this method is crucial since it boosts precision without overwhelming the system. When it comes to black hole mergers, simulations have to account for incredible gravitational forces. The collision of two black holes is one of the most violent events in the universe. As they approach each other, they emit gravitational waves, which ripple through space-time like waves on a pond. These simulations must track every twist and turn, showing how the black holes spiral together and eventually merge. After the merger, there's a ring-down phase, where space-time vibrates and gradually settles, emitting specific frequencies called quasi-normal modes that scientists can detect with instruments like LIGO and Virgo. These black hole mergers aren't just theoretical. The patterns in gravitational waves match predictions from simulations, confirming that we're on the right track with these models. LIGO's observations of merging black holes in 2015 brought the theory to life, and each new detection refines our understanding of black hole behavior. Even the recoil, or kick, from merging black holes, where the resulting black hole is pushed away from its original position, has been simulated and observed, giving us insights into how these massive objects interact. Simulating black holes requires tremendous computing power. Supercomputers like Blue Waters and Summit handle billions of calculations per second to recreate black hole dynamics. Some simulations run for weeks or even months, with scientists using parallel processing to split calculations across hundreds or thousands of processors. It's a process that takes time, energy, and patience. But the results give us a glimpse into the hidden workings of these cosmic giants. Even light behaves differently near black holes, and simulations help us understand these strange effects. Geodesic tracing, a technique that follows the path of light around a black hole, lets scientists model how photons loop and twist in the black hole's gravity. The result is a photon ring, a bright circle around the black hole where light loops multiple times before either escaping or getting pulled in. This photon ring is what we see in the famous Event Horizon Telescope image of the M87 black hole. The ring isn't the event horizon itself. It's light bending around the black hole's gravity, an effect that simulations predicted and the EHT confirmed. The Event Horizon Telescope, EHT, uses a technique called interferometry to combine data from telescopes worldwide. By merging light from each location, the EHT creates a global network with resolution sharp enough to image black hole shadows. The data is processed with advanced algorithms to recreate black hole images, letting us see shadows cast by the event horizon. This visual data aligns with simulation predictions, helping scientists verify their models with real observations. But the simulations don't just stop at imaging. They also reveal other insights, like how black holes form accretion disks. These swirling rings of gas and dust heat up as they spiral closer to the black hole, reaching millions of degrees. Simulations show that these disks are incredibly turbulent, with particles smashing into each other at high speeds. The energy from these collisions produces X-rays, which astronomers detect with space telescopes, giving us a window into the extreme environment around black holes. Additionally, simulations show that black holes have the ability to release very strong particle jets that can travel almost at the speed of light from their poles. The black hole's spin twists the magnetic fields, which release particles in huge streams as jets. These jets, which can stretch for thousands of light years in supermassive black holes, shape star formation and perhaps galaxies as a whole. The mathematics behind these simulations presents unique challenges, particularly near the singularity, where density becomes infinite. Regular calculations break down here, so scientists use methods like excision, where they remove the singularity from the grid to avoid undefined values. This workaround lets simulations focus on the event horizon and surrounding regions, where most observable effects occur. Coordinate transformations also help simplify the math. By changing the way distances and directions are measured, scientists can model black holes using coordinates that make calculations more manageable. Spherical and polar coordinates are common choices, as they align better with a black hole's shape than standard grid layouts. Each of these adjustments allows the simulation to run more smoothly and accurately, bringing us closer to a real picture of black hole behavior. The dynamics inside a black hole reveal strange effects, such as the warping of the event horizon. Simulations show that black hole event horizons aren't perfectly smooth. They can form bulges or twists due to intense gravitational interactions, especially in black hole mergers. These distortions affect the light and matter nearby, bending them in unique ways. As black holes spin, they create frame-dragging effects, twisting spacetime around them. This effect, predicted by relativity and confirmed through simulations, is especially pronounced in fast-spinning black holes. These frame-dragging zones pull in nearby material, creating a kind of cosmic whirlpool around the black hole. These simulations have also confirmed that merging black holes produce specific gravitational wave signatures, or tones, like a musical instrument. These frequencies, called quasi-normal modes, depend on the black hole's mass and spin, allowing scientists to determine these properties from gravitational wave data. It's like reading a black hole's signature, written in the ripples of spacetime. Simulations show that black holes with high spin can twist spacetime into complex shapes, affecting how nearby particles move. These rotations drag material along with them, creating a unique type of turbulence in the accretion disk. Matter heated to millions of degrees produces X-rays, which we can detect and study, confirming simulation predictions. Each of these advances, whether in gravitational wave signatures, frame-dragging effects, or photon rings, brings us closer to understanding black holes as more than just cosmic sinks. They're complex, dynamic entities that follow patterns predicted by math and confirmed by simulations, providing us with models that help decode some of the universe's most extreme environments. Mathematical models and simulations. Einstein's field equations might sound abstract, but they're at the core of what we know about black holes. They don't just give us numbers, they lay out how space and time twist, bend, and stretch under extreme gravity. These equations are complicated. 10 interlinked differential equations that connect mass, energy, and the curvature of spacetime. When Einstein published them in 1915, he probably didn't envision the future applications, but today they're key to understanding black holes. The complexity of these equations becomes more apparent as scientists apply them to black holes. Under certain conditions, the equations predict that spacetime can collapse into a point with infinite density, creating what we know as a black hole. Carl Schwarzschild was the first to solve these equations for a simple black hole, a non-rotating, perfectly spherical one. This solution, known as the Schwarzschild solution, defines the event horizon and predicts how light and matter would behave around it. But real black holes are rarely this simple. They rotate, they interact, and they collide with each other, requiring more complex solutions and, more often than not, computational help. For rotating black holes, the Kerr solution adds another layer. It describes how a black hole's spin distorts spacetime, creating a kind of cosmic whirlpool where space itself twists. This effect, known as frame dragging, is so powerful that it warps everything around the black hole, including light. The equations describing this rotation are far too complex to solve by hand, so scientists use computers to run simulations that capture these dynamics in detail. Creating a black hole simulation isn't just a matter of plugging numbers into a computer. Each black hole is broken down into tiny elements, like a grid overlaying space-time. Scientists calculate the gravitational pull on each point of this grid based on nearby points, updating these positions with each passing fraction of a second. This approach is called numerical relativity, where computers handle the massive calculations needed to keep up with Einstein's equations in real time. Finite difference breaks down the differential equations into small, manageable steps across the grid. Each step calculates changes in space-time, allowing scientists to create a time-lapse of black hole behavior. Another technique called adaptive mesh refinement focuses computing power on critical areas like the event horizon. This technique increases accuracy without overloading the system, which is essential when dealing with phenomena as complex as black holes. When it comes to black hole mergers, simulations have to account for incredible gravitational forces. The collision of two black holes is one of the most violent events in the universe. As they approach each other, they emit gravitational waves, which ripple through space-time like waves on a pond. These simulations must track every twist and turn, showing how the black holes spiral together and eventually merge. After the merger, there's a ring-down phase, where space-time vibrates and gradually settles, emitting specific frequencies called quasi-normal modes that scientists can detect with instruments like LIGO and Virgo. The patterns in gravitational waves match predictions from simulations, confirming that we're on the right track with these models. LIGO's observations of merging black holes in 2015 brought the theory to life, and each new detection refines our understanding of black hole behavior. Even the recoil, or kick, from merging black holes, where the resulting black hole is pushed away from its original position, has been simulated and observed, giving us insights into how these massive objects interact. Simulating black holes requires tremendous computing power. Supercomputers like Blue Waters and Summit handle billions of calculations per second to recreate black hole dynamics. Some simulations run for weeks or even months, with scientists using parallel processing to split calculations across hundreds or thousands of processors. It's a process that takes time, energy, and patience, but the results give us a glimpse into the hidden workings of these cosmic giants. Even light behaves differently near black holes, and simulations help us understand these strange effects. Geodesic tracing, a technique that follows the path of light around a black hole, lets scientists model how photons loop and twist in the black hole's gravity. The result is a photon ring, a bright circle around the black hole where light loops multiple times before either escaping or getting pulled in. This photon ring is what we see in the famous Event Horizon Telescope image of the M87 black hole. The ring isn't the event horizon itself, it's light bending around the black hole's gravity, an effect that simulations predicted and the EHT confirmed. The Event Horizon Telescope, EHT, uses a technique called interferometry to combine data from telescopes worldwide. By merging light from each location, the EHT creates a global network with resolution sharp enough to image black hole shadows. The data is processed with advanced algorithms to recreate black hole images, letting us see shadows cast by the event horizon. This visual data aligns with simulation predictions, helping scientists verify their models with real observations. But the simulations don't just stop at imaging. They also reveal other insights like how black holes form accretion disks. These swirling rings of gas and dust heat up as they spiral closer to the black hole, reaching millions of degrees. Simulations show that these disks are incredibly turbulent, with particles smashing into each other at high speeds. The energy from these collisions produces X-rays, which astronomers detect with space telescopes, giving us a window into the extreme environment around black holes. Simulations also reveal that black holes can emit powerful jets of particles, shooting out from the poles at nearly the speed of light. These jets come from magnetic fields twisted by the black hole's spin, launching particles out in massive streams. In supermassive black holes, these jets can extend for thousands of light years, influencing star formation and even shaping entire galaxies. The mathematics behind these simulations presents unique challenges, particularly near the singularity, where density becomes infinite. Regular calculations break down here, so scientists use methods like excision, where they remove the singularity from the grid to avoid undefined values. This workaround lets simulations focus on the event horizon and surrounding regions, where most observable effects occur. Coordinate transformations also help simplify the math. By changing the way distances and directions are measured, scientists can model black holes using coordinates that make calculations more manageable. Spherical and polar coordinates are common choices, as they align better with a black hole's shape than standard grid layouts. Each of these adjustments allows the simulation to run more smoothly and accurately, bringing us closer to a real picture of black hole behavior. The dynamics inside a black hole reveal strange effects, such as the warping of the event horizon. Simulations show that black hole event horizons aren't perfectly smooth. They can form bulges or twists due to intense gravitational interactions, especially in black hole mergers. These distortions affect the light and matter nearby, bending them in unique ways. As black holes spin, they create frame-dragging effects, twisting space-time around them. This effect, predicted by relativity and confirmed through simulations, is especially pronounced in fast-spinning black holes. These frame-dragging zones pull in nearby material, creating a kind of cosmic whirlpool around the black hole. Additionally, these models have proven that, similar to an instrument's tone, merging black holes create distinct gravitational wave fingerprints. Scientists may learn the mass and spin of a black hole from gravitational wave data because these frequencies, known as quasi-normal modes, are mass and spin dependent. Reading the signature etched in the waves of spacetime, it's like trying to decipher a black hole. Simulations demonstrate that black holes with a high spin may bend spacetime into intricate patterns, influencing how neighboring particles move. These revolutions drag material with them, resulting in a unique sort of turbulence in the accretion disk. Matter heated to millions of degrees emits X-rays that we can detect and investigate, validating modeling predictions. Each of these advances, whether in gravitational wave signatures, frame-dragging effects, or photon rings, brings us closer to understanding black holes as more than just cosmic sinks. They're complex, dynamic entities that follow patterns predicted by math and confirmed by simulations, providing us with models that help decode some of the universe's most extreme environments. What happens inside a black hole? Crossing the event horizon of a black hole means entering a place where the usual rules of physics just don't apply. Once you pass that boundary, the gravitational pull becomes inescapable, pulling you toward the center, toward the singularity. Every path, every direction, every possible movement leads straight to this center. It's not a choice, it's inevitable. No matter how much power you might have, there's no escape. Inside this region, the concept of time itself begins to twist and change. An observer watching from a safe distance would see you slowing down as you near the event horizon, your image fading as light from you gets stretched to wavelengths that eventually become invisible. This is due to a phenomenon called gravitational redshift, where light waves are stretched to longer, redder wavelengths by the intense gravity. From the observer's perspective, you seem frozen, locked in place at the edge. But to you, time still moves forward, even as space around you warps beyond recognition. Within this strange landscape, there's an effect called spaghettification. It's not just a poetic term. Spaghettification means that, due to the intense difference in gravitational pull between your head and feet, you would be stretched long and thin, like a piece of spaghetti. In smaller black holes, this stretching happens before you even reach the event horizon, but in supermassive black holes, with less extreme tidal forces near the boundary, you could actually cross the event horizon relatively intact, feeling the pull only after entering deeper inside. As you move closer to the singularity, the force of gravity intensifies, and the effects on time and space grow even more extreme. Some theories suggest that inside a black hole, space and time swap roles. This means that as you fall inward, moving forward in time literally brings you closer to the singularity. In other words, it becomes your unavoidable future. You can't change course, turn back, or even stop moving closer to the center, because time itself is carrying you towards it. The singularity, the center of the black hole, is where the math starts to fall apart. Density reaches infinity, and known physics simply doesn't work here. Some scientists think quantum effects might change this outcome, forming a Planck star rather than an infinitely dense point. But we still don't know. At the singularity, space-time as we understand it may no longer exist. Everything we know about the fabric of reality breaks down, suggesting that a new theory, possibly one that merges gravity and quantum mechanics, is needed. Then there's a radical idea that black holes might contain baby universes, separate regions of space-time branching out from the parent universe. In this model, matter pulled into a black hole could emerge as a new universe, existing in a separate space but connected through the black hole. It sounds like science fiction, but mathematically, it's possible. Such a universe would exist within the black hole, unreachable from the outside, but with its own distinct timeline and laws of physics. Speculations like the wormhole theory suggest that black holes might serve as connections to other universes, or even different parts of our own universe. The math suggests these connections could work, though a safe journey through them would be another matter. Some scientists propose a firewall might await anything entering a black hole, a high-energy barrier that destroys matter as it crosses the event horizon, eliminating any chance of reaching the singularity intact. Inside a rotating black hole, things could be even stranger. Instead of a single point, the singularity might form a ring, altering the black hole's structure. This ring-shaped singularity creates a space where normal cause and effect breaks down. Theoretical models predict that a Cauchy horizon could exist here, marking a boundary beyond which the usual rules of physics, like cause leading to effect, no longer apply. The future becomes unpredictable, leaving open questions about the fate of anything caught inside. Quantum entanglement might even connect particles near the event horizon with particles outside, hinting at links that stretch beyond the black hole's boundaries. This connection means that even though an object might be lost to the black hole, it could still have effects on particles far beyond it, creating a kind of cosmic bridge that science is only starting to explore. The issue of data retention also arises. According to classical physics, anything that falls into a black hole is dragged inexorably toward the singularity and then lost forever. Information cannot be destroyed, according to quantum physics. The now famous black hole information paradox emerged from this theoretical disagreement. Holographic principle and the edge of reality. The holographic principle is one of the most surprising ideas to come out of black hole studies. It suggests that all the information within a 3D region of space could actually be encoded on its 2D surface, almost like a hologram. This concept emerged from an unusual discovery in black hole physics. The amount of information a black hole can contain doesn't depend on its volume as we'd expect, but rather on the area of its event horizon. Physicist Jacob Bekenstein first noticed this strange connection in the 1970s, realizing that a black hole's entropy, a measure of disorder or information, was proportional to its surface area. This was groundbreaking because it defied the intuition that information should be stored within a volume, not on a surface. Building on this, Gerard 't Hooft proposed that if black holes store information on their surfaces, then perhaps our entire universe could work this way. Maybe everything we see, feel, and experience in 3D space is actually encoded on a distant 2D boundary, like a vast cosmic hologram. Leonard Susskind took these ideas even further, developing them into what we now call the holographic principle. He proposed that, in a sense, reality might just be a detailed projection from information stored on this boundary. This principle has profound implications for understanding reality, particularly when it comes to unifying quantum mechanics and general relativity. These two fields of physics describe different realms. Quantum mechanics governs the tiny subatomic world, while general relativity describes the massive gravitational world. But they clash in extreme environments like black holes, where both theories should apply. The holographic principle might be the link between them, suggesting that space and time themselves could be emergent rather than fundamental. In other words, space and time might not be as basic as they seem, but could instead arise from information on a 2D surface. One of the most fascinating aspects of the holographic principle is its potential to solve the black hole information paradox. According to quantum mechanics, information can't be lost, but if something falls into a black hole and is swallowed by the singularity, where does its information go? The holographic principle suggests that this information doesn't vanish. It could be encoded on the event horizon, preserved in some form, even if it seems lost inside the black hole. Another key piece of this puzzle is the anti-de Sitter conformal field theory, ADS-CFT correspondence, a concept developed by physicist Juan Maldacena. ADS-CFT shows that a theory of gravity in a higher dimension can be described by a theory without gravity on a lower dimensional boundary. This idea supports the holographic principle by providing a mathematical model for how a 3D space could be fully described by data on a 2D surface. Susskind and others used this model to argue that all information inside a black hole could indeed be represented on its boundary, preserving it even if it looks inaccessible from within. If the holographic principle holds true for black holes, it might apply to the entire universe. That could mean our three-dimensional experience of reality is just a projection from a boundary we can't directly observe. Everything we think of as physical might really be encoded on a distant surface, challenging the most basic ideas about the nature of existence. There's even speculation that dark energy, the mysterious force driving the accelerated expansion of the universe, might be tied to this holographic boundary. Some researchers suggest that interactions with this boundary could influence the universe's energy, potentially explaining why everything is moving apart faster over time. It's an idea that remains highly theoretical, but one that adds an intriguing dimension to our understanding of cosmic expansion. Experimental evidence supporting the holographic principle remains indirect but intriguing. Observations of black hole shadows, like the one captured by the Event Horizon Telescope, show how light bends near black holes in ways that echo this projection concept. Advances in particle physics, too, hint at behaviors that could align with the holographic view, especially as particles approach the smallest quantum scales. In experiments at CERN and other particle physics labs, scientists are pushing particles to near-light speeds, probing the limits where traditional space-time might start to look like a 2D boundary. Perception and awareness are other topics that the holographic principle brings up. What about the way we see things if reality is really a projection? Is our awareness confined to what is inscribed on an unseen surface, confined to what is projected upon it? This theory challenges not just our knowledge, but also our interpretation of the world around us. It touches on both physics and philosophy. The holographic principle suggests that what we consider real might be a thin slice of something larger, encoded on the very edges of our universe. This idea doesn't just reshape black hole theory. It forces us to rethink the universe and our place in it, opening doors to questions about existence, perception, and even the nature of reality itself. Quantum mechanics meets black hole theory. The holographic concept offers a fresh angle on the data loss process within a black hole. Like a cosmic memory stored on a 2D boundary, it implies that all the information and particles contained within a black hole might be imprinted on its surface. But quantum theory makes things more complicated by revealing that particles within black holes don't act in a conventional sense. Quantum mechanics and black hole theory don't get along very well. General relativity, the framework for understanding black holes, works for large objects and intense gravity. But when we look at the very small, quantum mechanics takes over. These two worlds have different rules, and when we try to combine them in a black hole, it leads to some puzzling contradictions. One of the most well-known issues is the black hole information paradox. The paradox starts with a simple rule in quantum mechanics. Information cannot be destroyed. Every particle, every piece of matter has information embedded in it. But in a black hole, anything that crosses the event horizon seems to vanish, pulled toward the singularity. In classical physics, that information should be gone forever. But this idea doesn't fit with quantum mechanics, where losing information breaks fundamental rules. Stephen Hawking's discovery of Hawking radiation in the 1970s added even more complexity. Hawking radiation occurs due to quantum fluctuations near the event horizon, where pairs of particles briefly appear, and one particle falls in while the other escapes. Over time, these escaping particles cause the black hole to lose mass and shrink. Eventually, if enough Hawking radiation escapes, the black hole would evaporate completely. But here's the catch. If the black hole evaporates, where does the information it swallowed go? Does it disappear with the black hole, or is it somehow preserved? Several ideas have been proposed to resolve this information paradox. One of them is the holographic principle, which suggests that all information inside a black hole could actually be stored on its 2D surface, the event horizon. If true, it means everything that enters a black hole is encoded as information on its surface, preserving it even if the black hole eventually evaporates. This way, information isn't lost, it's just encoded in a different form. Leonard Susskind and Gerard T. Hooft were two of the physicists who developed this idea, and it's led to a whole new way of thinking about black holes. Another theory, called black hole complementarity, suggests that information could exist both inside the black hole and on the event horizon. For an outside observer, information stays on the surface. But for an object falling in, that information is still present inside the black hole. This idea creates a sort of dual reality without violating quantum rules. Quantum entanglement may potentially offer a solution. When two particles become entangled, their relative positions are irrelevant to how changes to one particle influence the other. Certain researchers have postulated that even after colliding with a black hole, certain particles may remain entangled with those beyond the hole, keeping their data connected to the cosmos beyond. In this manner, data remains accessible through an invisible connection to the outside world, even if particles fall into a black hole. As far out theories go, there's the firewall hypothesis. A high-energy wall is said to form at the very edge of the event horizon in this scenario. To avoid having to account for data contained inside the black hole, anything that crosses it would be annihilated instantaneously. There are many who believe in the firewall idea, but it goes against certain fundamental physical laws and hasn't gained much traction just yet. In exploring what might happen to information in a black hole, scientists have looked to theories like loop quantum gravity. This theory suggests that space and time are made up of tiny loops, not continuous structures, creating a quantum core inside black holes rather than a singularity. This core could prevent matter from collapsing completely, providing a way to preserve information without violating quantum rules. Another model, the fuzzball theory from string theory, proposes that black holes might actually be made up of tangled strings rather than a singularity, storing information within their structure. But testing these theories is challenging. Black holes are incredibly distant and shielded by their event horizons, so observing their interiors directly is impossible. However, scientists can study gravitational waves, ripples in spacetime caused by black hole mergers. When two black holes collide, the waves they create carry information about their properties, and studying these waves helps us understand how black holes interact with spacetime at a quantum level. Hawking radiation itself is another challenge. It's a slow process. The radiation a black hole emits is incredibly faint, and for large black holes, it would take longer than the age of the universe for them to evaporate. Detecting Hawking radiation is beyond our current technology, but scientists are working on alternative ways to explore the effects it predicts. At the smallest scales, space-time may be foamy, filled with tiny fluctuations that affect how particles and forces behave. This idea of space-time foam suggests that space inside black holes isn't smooth, but full of constant tiny changes. Such a structure would mean particles can't reach infinite density, potentially preventing the formation of a true singularity. If black holes have these fluctuating foam-like structures inside, it could help explain how information is stored, and might even hint at a quantum structure of spacetime itself. Loop quantum gravity also introduces the idea of a Planck star, a dense core inside black holes where matter reaches maximum compression without collapsing into a singularity. Instead of an infinite density, the Planck star represents a stable state within quantum limits. If true, this model would mean that information is preserved in a compact form rather than being lost in an unreachable point. Some theories go even further, suggesting that particles approaching the black hole's singularity experience a bounce effect, essentially rebounding before reaching infinite density. This rebound would prevent total collapse, conserving information while maintaining the black hole's gravitational pull. The bounce effect is purely theoretical, but it hints at possibilities that might one day change how we understand the deepest reaches of black holes. In quantum mechanics, entangled particles can stay linked no matter how far apart they are, raising the idea that particles inside a black hole could still be connected to particles outside. This connection could allow information to leak from inside the black hole in subtle ways, maintaining the link with the outside universe and bypassing the paradox. Each of these ideas, from entanglement to loop quantum gravity, firewalls to fuzzballs, tackles a small part of the black hole information paradox. And while they don't provide all the answers yet, they show how scientists are rethinking the laws of physics to try and understand what happens to matter, energy, and information in a black hole's powerful gravitational field. As we study these mysteries, it's becoming clearer that black holes are more than simple gravitational sinks. They're windows into the fundamental nature of reality, revealing possibilities for how information, time, and space itself might behave at the universe's limits. Cosmic inflation and black hole origins of the universe. Cosmic inflation suggests that our universe, once smaller than an atom, expanded at an unimaginable rate in the tiniest fraction of a second. Alan Guth first proposed this idea in 1980 as a way to explain why the universe looks so smooth and flat. This rapid expansion, or inflation, would stretch space itself, smoothing out any irregularities and explaining why the universe appears so uniform when we look at it on a grand scale. The question is, why would something expand this fast in the first place? And why did it stop, allowing the universe to grow at a much slower rate afterward? The theory of cosmic inflation helps solve what physicists call the horizon problem. Without inflation, distant regions of the universe wouldn't have had time to exchange light or heat, so we'd expect them to look vastly different. But they don't. They look nearly identical in temperature, suggesting they somehow did interact. Inflation explains this by proposing that those distant regions were once close enough to interact before the rapid expansion pulled them far apart. Inflation doesn't just explain why the universe is smooth and even. It also offers insights into why galaxies and other structures formed the way they did. During inflation, tiny quantum fluctuations, small random changes at the smallest scales, were stretched out into larger patterns. These fluctuations became the seeds for galaxy clusters, creating the structure of the universe we see today. The cosmic microwave background, or CMB, contains faint traces of these original patterns, supporting the idea that inflation shaped the early universe. Some scientists propose that our universe itself could have originated from a black hole in a larger universe. According to this idea, what we see as the Big Bang might have been the formation of an event horizon, from the perspective of an outside universe. From our point of view, this looked like a rapid inflationary period, but it could also resemble how a black hole's event horizon grows when it pulls in matter. In this black hole universe view, our universe's boundary could behave like an event horizon, containing all the information within it. Just as black holes trap information on their surfaces, the universe might work similarly, storing all data about its contents on a cosmic boundary. This aligns with the holographic principle, which suggests that everything inside the universe could be a projection from information encoded on its surface. The possibility that inflation is ongoing in other parts of the universe is also being considered by some physicists. This fits within the framework of the eternal inflation theory, which maintains that the formation of new bubble universes continues even after inflation ends in certain places. Like our own universe, these bubbles would expand during an inflationary phase, but they would each exist in their own pocket of space. Each bubble universe in this idea might have its origins in a black hole in a parent universe, and ours is only one among many. How inflation might connect to black holes. Physicists have studied what happens to matter and energy as they approach a black hole's singularity. The immense energy from quantum fluctuations during inflation could mirror conditions near a black hole's event horizon, where space-time stretches and bends. This similarity has led some scientists to wonder if black holes within our universe might produce new universes inside them, each beginning with its own form of inflation. Inflation also leaves behind clues in the form of gravitational waves, ripples in space-time caused by massive cosmic events. These waves, detected by instruments like LIGO, provide indirect evidence of inflation by revealing how space responded to extreme events in the early universe. Primordial gravitational waves, created during the inflationary phase, could help us understand how inflation works and whether it aligns with the black hole universe hypothesis. Detecting these waves is challenging, but each discovery brings us closer to understanding the forces that shaped our universe. There's also a theory called the Big Bounce, which suggests that our universe's expansion might be part of an endless cycle. In this model, the universe expands, then contracts, only to bounce back in a new Big Bang-like event. Some scientists believe that black holes might play a role in this cycle, with each contraction possibly forming a singularity that leads to a new expansion. If true, black holes could be integral, not just to our universe's beginning, but to cycles of creation that may have happened many times before. Understanding inflation also brings up questions about quantum mechanics. During inflation, quantum fluctuations affected everything in the universe. These fluctuations could provide insight into how black holes behave on a quantum level. In particular, they hint that space-time itself might have quantum foam at very small scales, with tiny fluctuations constantly shifting and affecting particles. This foam might even prevent singularities from forming, limiting the density of matter inside black holes and possibly offering clues about what sparked inflation in the first place. Some have proposed that inflation might have been triggered by a quantum vacuum state, a condition where energy levels are so low that random fluctuations can lead to sudden, massive expansion. This concept connects directly to black hole physics, where energy fluctuations near an event horizon could drive similar space-time stretching. It suggests that the same principles underlying inflation might also explain how black holes influence space around them. The idea of a baby universe forming inside a black hole also offers a fascinating perspective. According to this theory, when matter and energy enter a black hole, they might compress until they create conditions similar to the Big Bang. Inside the black hole, a new universe could emerge, expanding with its own version of inflation. In this view, each black hole could act as a cosmic seed, creating entire universes with unique properties and laws of physics. The eternal inflation model and black hole universe theories raise the possibility of a multiverse, a collection of countless universes, each with its own distinct characteristics. If every black hole leads to a new universe, then the universe we live in might just be one branch in an infinite network of realities. It's a concept that pushes the boundaries of what we consider possible, suggesting that black holes are not just ends, but also beginnings. One of the toughest questions is figuring out what initially caused inflation to start. Observing or replicating inflationary conditions in a lab is nearly impossible due to the extreme energy levels involved. But researchers are getting creative, using mathematical models and simulations to understand what might trigger such rapid expansion. We can't observe what happens inside black holes directly, and inflationary conditions are far beyond our reach. However, scientists are hopeful that by studying the cosmic microwave background and gravitational waves, they can gather clues about the inflationary phase. Each new piece of data could reveal more about the origins of our universe, and possibly the role black holes play in creating entire worlds. Inflation, with its roots in quantum fluctuations, black hole dynamics, and the rapid growth of space, remains one of the most mysterious aspects of the early universe. Dark matter and dark energy, possible clues. Dark matter too might have unexpected connections to black holes. Some scientists propose that dark matter could be made up of primordial black holes, which would have formed in the early universe. Unlike typical black holes that form from collapsed stars, primordial black holes would have formed right after the Big Bang. These black holes would act like dark matter because they exert gravity but don't emit light, behaving in ways that are almost indistinguishable from dark matter particles. Dark matter and dark energy are two of the biggest mysteries in our universe. Together, they make up about 95% of everything, yet they remain hidden from our view. Dark matter doesn't emit or absorb light, which makes it invisible, but we know it's there because of its gravitational effects. It's what holds galaxies together, providing the extra gravity needed to keep them intact as they spin. Without dark matter, galaxies would fly apart, as visible matter alone doesn't have the gravitational pull to hold them together at the speeds they're rotating. One leading theory is that dark matter consists of particles called WIMPs, weakly interacting massive particles. These particles would have mass, giving them gravitational influence, but they don't interact with light or other particles in a way we can detect. Experiments all over the world are searching for WIMPs, hoping to catch a glimpse of these elusive particles. Other theories suggest dark matter might be made of axions, particles so light they act more like waves than particles. Axions would create a kind of invisible fog that wraps around galaxies and helps bind them together. Another dark matter candidate is the sterile neutrino, a particle that doesn't interact with any other particles except through gravity. These particles could be floating through our universe without us ever noticing, influencing only the mass and structure of galaxies. Some scientists even propose that dark matter might be coming from extra dimensions, exerting gravitational influence from spaces beyond our own, affecting our universe in subtle but powerful ways. Dark energy, a force that's even more mysterious than dark matter. Dark energy makes up about 68% of the universe, and it's the reason galaxies are moving away from each other faster and faster. Unlike gravity, which pulls objects together, dark energy acts as a repulsive force, pushing galaxies apart. Scientists discovered this when they observed distant supernovae and found that galaxies were receding at accelerating rates, something only a force like dark energy could explain. Some physicists think dark energy might not be an actual substance, but a property of space itself, like a constant background energy. This idea goes back to Einstein's cosmological constant, a term in his equations that represents a fixed amount of energy in empty space. There's also debate about whether dark energy is constant over time or if it might change, potentially accelerating or slowing down in the future. According to certain hypotheses, dark energy might originate in another universe. Within this theory, dark energy originates in higher dimensional space via gravitational leakage from nearby universes. Picture our cosmos as a three-dimensional brain suspended in a four-dimensional bulk. The force we perceive as dark energy may really be a product of influences from neighboring brains that exert an impact on our cosmos. In this framework, dark energy could be like a pressure from an external source, pushing outward on our universe. It might even come from interactions at the boundary of our universe, hinting at an edge effect from a multiverse. If true, dark energy would offer indirect evidence of extra dimensions and might suggest our universe isn't as isolated as we once thought. Black holes might even create dark matter-like effects through interactions with quantum fields. These interactions could increase their gravitational influence, creating regions around them that mimic the effects of dark matter. If this is true, it could mean that dark matter might actually be trapped matter from previous cycles of the universe, compressed into black holes that act as invisible anchors. Some alternative theories propose that dark matter and dark energy could be two sides of the same coin. In this view, they would be different manifestations of an unknown force or particle that operates in ways we don't yet understand. The modified Newtonian dynamics, Mond theory, for example, suggests that our understanding of gravity might be incomplete. Mond proposes that gravity itself changes at large scales, creating effects that look like dark matter without needing any invisible particles. Others think dark energy could be a remnant of high-energy processes from the universe's creation. It might be leftover energy from black hole mergers or other intense events, dispersed across the universe as a kind of background force. This would mean that dark energy is a relic of ancient cosmic activity, possibly tied to the early phases of black hole formation. Dark matter and dark energy could even represent shadow versions of ordinary matter and energy, existing in a parallel form that we can't detect directly. This shadow matter might interact with our universe only through gravity, creating an invisible structure that holds everything together and drives expansion. Scientists are exploring various methods to detect dark matter and dark energy. Detectors on Earth aim to capture particles like WIMPs by observing their rare interactions with normal matter. So far, no definite detections have been made, but each experiment provides valuable data. Observations of galaxy rotation curves also give indirect evidence of dark matter, since galaxies rotate faster than visible matter alone can account for. Dark energy's effects are measured through redshift, where light from distant galaxies shifts to longer wavelengths as space expands. The cosmic microwave background, the afterglow of the Big Bang, also reveals clues about dark matter, as its gravitational influence affects temperature fluctuations across the sky. These mysteries have big implications for the idea that our universe could be like a black hole. If dark energy is influenced by an outside universe, it could suggest that our universe behaves like a black hole, with expansion driven by interactions with a larger space. The structure of dark matter might hint at our universe's edge, behaving like an event horizon, with dark energy pushing outward, much like a black hole's boundary expands as it consumes matter. Dark energy's consistent effects across vast distances resemble the gravitational pull of a black hole's event horizon, hinting that there may be a deeper connection. Some scientists even speculate that black holes could serve as gateways between universes, with dark matter and dark energy providing clues to these connections. The distribution of dark matter in galaxies mirrors how matter clusters around black holes, suggesting there may be a link between their origins. It's as if dark matter gathers in patterns that reflect a hidden gravitational structure, much like black holes shape space around them. The James Webb Space Telescope and other advanced observatories could reveal new insights by observing galaxies and supernovae at extreme distances. Improved gravitational wave detectors might also uncover more about dark matter if primordial black holes are found to produce detectable space-time ripples. In labs, scientists are trying to simulate early universe conditions to see if they can recreate the processes that may have led to dark matter and dark energy. Studies of galaxy collisions reveal how dark matter behaves in massive interactions, as dark matter appears less affected than regular matter in these cosmic encounters. Dark matter and dark energy remain mysteries, but each new discovery pulls back the curtain just a bit more. As we learn more, These invisible forces may help us understand not only the structure of our universe, but also its relationship to black holes, higher dimensions, and perhaps even other universes. The event horizon and observational evidence. While dark matter and dark energy are invisible forces shaping the cosmos, the event horizon of a black hole gives us a direct boundary to study these mysteries. Just as dark matter creates invisible structures that hold galaxies together, and dark energy pushes the universe to expand, black holes hold clues about forces and structures we can't see, but can observe indirectly. Of all the things about black holes, the event horizon is the most mysterious. It's not quite a wall or surface, but it does serve as a barrier. At that point, not even light can evade the overwhelming force of gravity, and there's no going back. For this reason, black holes seem black. We have no idea what's on the inside looking in. Still, scientists keep their attention focused on the event horizon, because it may provide hints about what's going beyond it. The Event Horizon Telescope, EHT, has allowed us to see something that was once only theoretical, the shadow of a black hole. In 2019, it captured the first image of the supermassive black hole at the center of the galaxy M87. This image, showing a glowing ring surrounding a dark center, provided a direct glimpse of a black hole's event horizon. The dark spot isn't the black hole itself, but the shadow created by the event horizon blocking light. The bright ring around it is made of hot gas and particles swirling at nearly the speed of light, emitting light that the EHT could capture. What makes this image so important is how it confirms predictions from Einstein's general relativity. Light bends around the black hole, creating that distinctive ring as gravity warps the path of photons traveling near the event horizon. This bending of light, called gravitational lensing, is extreme near a black hole, where the gravitational pull distorts space itself. For the EHT to capture this effect at such a distance, it combined data from radio telescopes worldwide, creating a virtual telescope as big as Earth. This enormous lens allowed us to see details as small as the event horizon of a black hole 55 million light-years away. The details within the EHT images go even deeper, revealing structures known as photon rings. These rings are created by photons that have orbited the black hole one or more times before escaping, creating multiple layers in the image. Each ring is slightly brighter and represents light that has been bent to different degrees by the black hole's gravity. These rings provide insight into how information might be layered near the event horizon, suggesting a complex structure rather than a simple edge. The photon rings support theories like the holographic principle, which proposes that everything inside a black hole could be stored on the event horizon, much like a hologram encodes a 3D image on a 2D surface. This concept connects to the idea that the universe itself might have an event horizon, where all the information about our reality is stored on a distant boundary. If black holes work this way, then our entire universe could be structured similarly, existing as a kind of projection from this cosmic boundary. Black hole images also help us explore the idea that our universe might behave like a black hole's interior. In this theory, the observable universe could be a kind of event horizon within a much larger cosmos. Just as light bends near a black hole, the large-scale structure of space-time in the universe might also lens light due to its mass and shape. This lensing effect would resemble what we see around black holes, but on a cosmic scale, hinting that our universe might be structured similarly. A fascinating aspect of the EHT's findings is the accretion disk, which is a ring of dust and gas that envelops the event horizon of the black hole. A high-energy zone that generates X-rays and radio waves is formed as particles spiral inward, heating this disk to millions of degrees. By analyzing these emissions, researchers can learn more about black holes' feeding habits and the effects they have on their surroundings. Nearby stars and gas are impacted by the high energy from accretion disks, which in turn influence the cosmic landscape and the development of galaxies. The behavior of these accretion disks also suggests that black holes might recycle matter. As matter spirals into the black hole, it breaks down under extreme conditions, Some particles are ejected in jets that shoot out from the black hole's poles at nearly the speed of light, while other particles are drawn into the event horizon. This recycling of matter and energy shows how black holes aren't just cosmic traps. They actively shape their surroundings. The Event Horizon Telescope has made it possible to study these high-energy jets in detail. By observing the magnetic fields near the event horizon, scientists can see how black holes generate these jets and how they affect interstellar space. These jets extend for thousands of light years, carrying particles and magnetic fields that interact with the galaxy around them. The jets can even influence the rate of star formation, showing that black holes play a central role in galactic ecosystems. As scientists improve imaging techniques, they hope to observe these jets in real time and study how they change over time. Future upgrades to the EHT, like adding space-based telescopes, could reveal even finer details of black holes, helping us understand how different sizes and spins of black holes affect their event horizons. Each new observation could reveal more about how black holes interact with their environments and how they impact the universe on large scales. Observing the event horizon also allows scientists to test ideas about the information stored around black holes. Since each photon ring in a black hole image contains light that has orbited the black hole multiple times, it could carry data about the matter and energy that have passed into the black hole. This layering of photon rings suggests that information might be preserved in the light that orbits the event horizon, possibly encoding details about everything that has crossed it. Some researchers speculate that the event horizon might act as more than just a boundary. It could be a bridge to other universes. In multiverse theories, black holes could act as connections between universes, with information crossing over or even creating new universes in the process. Observing how photon rings form and interact might help us understand if black holes are connected to other realms or dimensions, providing clues to the larger structure of the multiverse. The EHT's observations have brought us closer to understanding black holes, but they also raise questions about our universe. If black holes can store information on their event horizons, could our universe itself be a massive storage of information on a cosmic boundary? This possibility aligns with theories that suggest our reality might be a hologram, a projection of data encoded on a distant surface. Black hole images, with their intricate photon rings and bending light, offer a glimpse into how this might work, suggesting that what we see might be only a part of a much larger structure. Each new discovery from the EHT provides fresh evidence about the nature of black holes, hinting at connections to the fundamental structure of the universe. With each observation, we're learning more about how black holes bend, store, and manipulate light and matter, revealing details that could connect to the mysteries of dark matter, dark energy, and even the possibility that our universe functions like the interior of a cosmic black hole. Could our universe be a black hole's interior? While black hole images help us explore hidden boundaries in our universe, the idea that our universe itself could be inside a black hole takes this even further. This theory suggests that our entire cosmos might exist as the interior of a black hole in a much larger space. Just as light and matter can't escape from a black hole's event horizon, our universe might be similarly bound by a cosmic horizon, a limit beyond which we cannot observe or reach. Supporters of this theory point to the structure of our universe as surprisingly similar to the inside of a black hole. For instance, just as black holes have an event horizon, we have a cosmic horizon, a boundary that limits our view of the universe because light from beyond it hasn't had enough time to reach us. Inside black holes, space and time are distorted under intense gravity, and our universe also shows signs of space-time curvature on a grand scale. These similarities make it possible to consider that our universe might be an inner region of a much larger black hole structure. One argument for this theory is that the Big Bang might not have been a singular starting point. Instead, it could have been the moment when a black hole formed in a higher dimensional space, creating our universe as its interior. This theory proposes that the rapid inflation of space right after the Big Bang might reflect how a black hole's event horizon expands as it pulls in more matter. In other words, the inflation we observe could mirror the stretching effect seen around a black hole. If we really are inside a black hole, it could also help explain why our universe behaves according to both general relativity and quantum mechanics. These theories often conflict, but within a black hole, they both play crucial roles. The gravitational effects of relativity describe how black holes warp space and time, while quantum mechanics explains the microscopic properties of particles. A black hole-like universe could unify these two perspectives, showing that our reality is shaped by both on different scales. Beyond the event horizon of a black hole, space and time may switch roles. That means time moves forward like space does, with everything inevitably progressing toward the singularity. Some scientists speculate that this swap might explain why time in our universe appears to flow forward, toward what we perceive as a future we cannot avoid. The holographic principle also aligns with the black hole universe hypothesis. This principle suggests that everything inside a black hole can be represented on its event horizon, like a 3D image encoded on a 2D surface. If this is true, then our entire universe might be encoded on a cosmic boundary, and we are experiencing it as a projected reality from this boundary. Observing black holes gives us a glimpse of how such a structure could work, offering a model that might reflect the nature of our entire universe. Some scientists point to the cosmic microwave background, CMB, as potential evidence. The CMB shows us a snapshot of the universe when it was young and hot, and its smoothness and uniformity could hint that our universe started from a highly compressed state, similar to conditions inside a black hole. Patterns in the CMB reveal how matter was distributed in these early stages, and studying these patterns may give clues about whether our universe's origins align with a black hole's interior. The speculative side of this theory draws from brane cosmology and string theory. In these models, our universe could be a 3D brane inside a higher dimensional black hole, meaning we are just one layer within a larger multidimensional cosmos. Some theories in string theory, like M theory, even propose that black holes could act as portals to new realms. If black holes create their own inner universes, then each black hole could represent a unique universe with its own physical laws. The bounce theory also supports the black hole universe idea. According to this model, a black hole compresses matter, but instead of collapsing into an infinitely dense singularity, the matter rebounds, creating a new universe in the process. In this view, each black hole could act like a cosmic recycling process, continuously creating new universes from old ones. Of course, there are significant challenges and barriers to proving this hypothesis. We currently lack the ability to observe higher dimensions directly, and the extreme conditions within black holes make it nearly impossible to collect direct data about their interiors. Experimental verification would require technology far beyond what we have, as the energy needed to simulate or observe a black hole's interior exceeds anything we can generate. Critics of the black hole universe theory argue that if we were inside a black hole, we would observe stronger gravitational effects, similar to the intense gravity around a black hole's event horizon. Others point out that black holes typically have a singularity at their center, while our universe appears to be isotropic or uniform, with no observable center. This difference in structure raises questions about how a black hole-like model could explain the vast, even distribution of galaxies in our universe. If our universe were inside a black hole, some argue we should detect signals of an outer boundary, like an event horizon. Yet, we don't observe any clear evidence of such a boundary in our cosmic measurements. Others note that black holes cause extreme time dilation near their event horizons, while time in our universe flows at a relatively stable rate without the intense slowing effect expected near a black hole. Testing the black hole universe theory remains difficult due to these limitations. However, future technologies may bring us closer to finding answers. As we build more sensitive gravitational wave detectors, such as those at LIGO, we might detect signals that mimic conditions inside black holes. Improved AI-driven simulations and quantum computing might also allow us to model black hole interiors in greater detail, providing insights into whether such conditions could match our universe's properties. If this theory holds any truth, the philosophical implications are vast. It suggests that reality as we know it might be a projection from a larger hidden cosmos. Universes might be nested, with each black hole giving rise to a new reality, and the black holes within our universe could be creating new child universes as well, creating an endless chain of creation. This also connects with simulation theory, where our experience of reality might be just one layer of a more complex, deeper structure within a black hole. Then the creation of our universe wasn't a singular, unique event. Instead, it could be part of an ongoing cosmic process. Rather than a single Big Bang, this model suggests that universes are born repeatedly through the creation of black holes, with each black hole spawning a new cosmos, possibly with its own unique physical laws. While the black hole universe theory remains speculative, it continues to inspire new questions and possibilities about the origins of our cosmos. Observing black holes, analyzing cosmic backgrounds, and advancing technology may someday offer hints about whether our universe is indeed a cosmic interior. Leading scientists and their contributions. As we explore the possibility of our universe existing within a black hole, it's important to recognize the trailblazing scientists whose theories, experiments, and ideas brought this concept into mainstream discussion. Their work redefined our understanding of black holes, expanding beyond gravitational sinks to something far more complex. Structures with the potential to create entire universes. One of the first to delve into these ideas was John Archibald Wheeler, a physicist who coined the term black hole and explored concepts like quantum foam, where space-time fluctuates at the smallest scales. Wheeler's idea that reality arises from fundamental bits of information, a concept he called it from bit, suggested that information might shape our universe. This view opened the door to ideas like the holographic principle, where information within a black hole could exist on its boundary, hinting that our universe's reality might be similarly encoded. Leonard Susskind expanded on Wheeler's insights with his work on the holographic principle. Susskind proposed that everything happening inside a black hole could be represented as a projection on its boundary, the event horizon. This idea not only altered our understanding of black holes, but also implied that the entire universe could be a kind of holographic projection, possibly existing within a black hole in a higher dimensional space. Adding to these discussions was Gerard 't Hooft, a Dutch physicist who further developed the holographic principle. His work suggested that information within a black hole is preserved rather than lost, challenging earlier assumptions and supporting the possibility that our universe's information might be stored on a boundary, much like in a black hole. Together, 't Hooft and Susskind's insights strengthened the theory that our universe could be encoded on a larger cosmic surface. Stephen Hawking contributed significantly to these discussions with his discovery of Hawking radiation. This showed that black holes aren't just isolated, unchanging objects. They emit radiation and slowly lose mass over time. Hawking's work on black hole thermodynamics revealed a paradox about information loss, leading to debates with Susskind and others on whether black holes destroy information. This question of information preservation became central to understanding whether black holes could create new universes, and whether they might function as gateways to alternate realms. In the realm of speculative physics, Nikodem Poplawski proposed that black holes might not lead to singularities, but could instead create new universes. His work is based on the Einstein-Cartan theory, which suggests that black holes spin and create a form of torsion that prevents infinite density, potentially causing a rebound effect. Poplawski's idea that each black hole might give birth to a new universe within it aligned closely with the black hole universe hypothesis, providing a mathematical foundation for how such a process might work. Physicist Lee Smolin took these ideas in a new direction with his cosmological natural selection theory, proposing that black holes create new universes with slight variations in physical laws. Smolin suggested that the universe could function similarly to biological evolution, where black holes produce new cosmoses in a kind of natural selection for universes that favor black hole formation. His theory aligns with the idea that black holes could be seeds for new realities, giving a unique perspective on how our universe might have emerged within a black hole. Roger Penrose offered another take with his conformal cyclic cosmology, CCC theory, which proposes that universes cycle endlessly, with each universe beginning where the previous one ends. Though not directly supporting the black hole universe hypothesis, Penrose's work on the cyclical nature of universes suggests that black holes might play a role in this ongoing process, potentially resetting space and time to create new realities. Alan Guth provided an essential piece of the puzzle with his inflation theory, which describes how our universe expanded rapidly after the Big Bang. While Guth didn't directly propose the black hole universe model, his inflationary theory showed how space can stretch dramatically in a short period, resembling how a black hole's event horizon might expand as it consumes matter. This connection between inflation and black holes continues to influence discussions on how our universe's rapid expansion could mirror black hole dynamics. In addition to theoretical work, significant experimental advances have strengthened these concepts. The Event Horizon Telescope, EHT, captured the first ever image of a black hole's event horizon, confirming predictions from general relativity about how light bends around black holes. By imaging the supermassive black hole in galaxy M87, the EHT provided a real-world example of a boundary where information might be stored, reinforcing holographic theories that suggest our universe could work similarly. The discovery of gravitational waves by the LIGO Observatory also plays into these ideas. Gravitational waves, created by black hole collisions, carry information about black hole properties that might help us understand if such extreme environments could lead to the formation of new universes. With each detection, scientists gather more data on black hole dynamics, moving us closer to understanding if black holes could be more than just massive gravitational fields. Debates among these scientists have pushed black hole research forward. For example, Hawking and Susskind famously disagreed over the black hole information paradox. Hawking initially believed that information entering a black hole was lost forever, while Susskind argued that information is preserved on the event horizon. This debate ultimately led Hawking to reconsider, supporting the idea that black holes may retain information, which could potentially influence new universe formation. Gerard 't Hooft and Leonard Susskind also had an influential debate on the nature of holography. While both agreed that black holes store information on their boundaries, they differed on how this process worked. Hooft's approach leaned toward mathematical models, while Susskind focused on physical implications, each adding depth to the holographic model and its applications to our universe. These scientific debates have not only expanded our understanding of black holes, but have also influenced broader philosophical questions about reality. The idea that we might live within a black hole challenges traditional concepts of the universe as a single, isolated entity. It suggests that our cosmos could be part of a larger, multi-layered reality, with each black hole potentially creating a new child universe. Some of these theories also connect to simulation theory, where our universe might be a projection or hologram from a deeper reality. If black holes function as boundaries where information is encoded, then our entire universe could be a kind of cosmic simulation, with all physical events unfolding according to data encoded on a larger hidden surface. The idea that black holes might create new universes also implies that the Big Bang may not have been a unique, singular event. Instead, our universe could be part of a cycle, where each black hole generates a new cosmos, each with its own distinct physical laws. This model of nested universes suggests an ongoing process of universe creation, with black holes as the engines driving new realms. These contributions by physicists and researchers have led to a new way of looking at black holes, not as cosmic endpoints, but as bridges to unexplored realities. The combination of experimental data, theoretical models, and philosophical insights continues to shape our understanding of black holes. Challenges to the black hole universe hypothesis. As we can see, the idea that our universe could exist within a black hole has captivated scientists and the public alike. From fascinating scientific contributions to detailed theoretical models, it seems like the pieces might align for a cosmic structure where black holes act as gateways to new realms. However, despite the appeal and elegance of the concept, not everyone in the scientific community is convinced. Numerous challenges and critiques stand in the way, raising tough questions about the hypothesis. For some, the universe inside a black hole model is compelling, but falls short under closer scrutiny. So, what are the key obstacles that prevent widespread acceptance of this theory? For starters, there's the issue of direct evidence. Currently, no observations suggest we're within a larger black hole structure. We observe stars, galaxies, and cosmic phenomena, but none of these directly point to the presence of a surrounding black hole boundary. One core argument against the theory is the lack of an observable event horizon. In a black hole, the event horizon is an unmistakable boundary where gravity's pull is so strong that nothing, not even light, can escape. If our universe were inside a black hole, we might expect to see some equivalent of this event horizon. Yet, we don't observe any cosmic structure that behaves like such a boundary. Our universe seems to stretch on, expanding, but with no sign of an outer edge acting as a gravitational barrier. Another challenge is that gravity within our universe doesn't match the intense gravitational effects expected inside a black hole. Near a black hole's event horizon, gravity warps space-time so dramatically that it causes extreme time dilation. Time slows down drastically as you approach the boundary. But in our universe, time flows relatively evenly. This consistency doesn't align with the strong gravitational pull a black hole would impose if we were inside one. The uniform structure of our universe also raises questions. Our universe is isotropic, meaning that matter is spread out uniformly in all directions. Black holes, on the other hand, are not known for such smoothness. Matter inside them would be drawn toward the center, rather than remaining evenly spread out. This contrast between our universe's even distribution of matter and the chaotic interior we'd expect inside a black hole creates a fundamental difference that's hard to overlook. One of the most direct challenges comes from the absence of a singularity. In a typical black hole, gravity pulls all matter inward toward a central singularity, a point of infinite density. But our universe doesn't have a discernible center or a single focal point where all matter is drawn. We observe a vast, expanding universe with no obvious center, which is difficult to reconcile with the structure of a black hole. Critics also point to the inconsistencies in expansion rates. Our universe has been expanding at an accelerating rate, driven by dark energy. However, this rate of expansion doesn't match the predicted growth rate of a black hole's event horizon. If we were inside a black hole, we might expect to see a different pattern of growth, one that mirrors how black holes behave as they consume more mass. Yet the acceleration we observe appears to contradict the expected behavior inside a black hole. Speaking of dark energy, its role complicates things further. Dark energy drives the expansion of the universe, pushing galaxies apart. Inside a black hole, gravity reigns supreme, pulling everything inward toward the center. So the existence of a force that actively pushes space apart is difficult to reconcile with the idea that we're within a black hole, where we'd expect gravity, not a repulsive force, to be dominant. The differences between the Big Bang and a black hole singularity add to the skepticism. The Big Bang is understood as a rapid expansion from an incredibly dense and hot state, whereas black hole singularities pull matter inward, compressing it toward a point. If our universe came from a black hole, it's unclear how this shift from compression to expansion would occur. The Big Bang and black hole singularity are fundamentally different in nature, creating another gap in the theory. Hawking radiation poses another challenge. Black holes slowly lose mass over time as they emit Hawking radiation, eventually shrinking as they release energy. If our universe were inside a black hole, we might expect some similar kind of energy loss, or an indication that our universe's boundaries are slowly shrinking. However, our universe is expanding, with no sign of energy loss from a boundary, suggesting we might not be within a black hole. Then there's the paradox of size. Our universe is vast, stretching billions of light years across, while black holes are much more compact. The scale of our observable universe seems incompatible with what we'd expect if it were confined within a black hole. This size paradox presents a fundamental mismatch between the structure of black holes and the scale of our universe. From a theoretical standpoint, general relativity presents issues when applied on such large scales. While general relativity explains gravity well on cosmic scales, it doesn't imply that expanding universes could exist within black hole boundaries. Quantum mechanics, too, presents problems, as it doesn't naturally align with the black hole universe model, particularly around the preservation of quantum information across such a vast space. The theory also faces challenges around extra dimensions. Hypotheses that place our universe in a higher dimensional black hole remain speculative, as we have no way to observe or interact with these extra dimensions. Without direct evidence of higher dimensions, the idea of a universe within a larger black hole remains theoretical, and without empirical support, it's difficult to fully accept. Entropy paradox. Black holes are thought to increase in entropy over time, which is a measure of disorder or information. But our universe also has its own entropy, which grows as it expands. The parallel growth of these entropies, one within the black hole and one within our universe, creates a complex question. How can two entropic systems coexist if one is inside the other? Critics also argue that alternative explanations for inflation weaken the need for a black hole model to explain our universe's expansion. Inflationary theories provide a well-supported explanation for why the universe expanded rapidly in its early moments, and these models don't require a black hole framework. Without a clear necessity for a black hole to explain inflation, some see it as an unnecessary complication. And then there's the issue of cosmic horizons. In the black hole universe hypothesis, cosmic horizons might be seen as the boundaries of a black hole, but cosmic horizons are simply limits set by the speed of light and the age of the universe. These horizons don't necessarily point to an outer event horizon, but rather represent the limits of what we can observe based on light's travel time. Philosophically, the idea of nested universes within black holes creates paradoxes. If every black hole produces a universe, then an infinite number of nested universes would form within each other, a concept that feels both untestable and endless. This infinite nesting of universes raises philosophical questions that blur the lines between science and speculation, complicating the theory even further. Many scientists argue that the theory lacks clear, testable predictions. Science relies on falsifiability, the idea that theories must make predictions that can be tested and potentially disproven. The black hole universe hypothesis struggles with this, as it doesn't provide clear ways to test or disprove it. Without testable predictions, it remains a largely speculative concept with limited potential for empirical verification. Each of these critiques highlights the complexities and gaps in the black hole universe hypothesis. While it's a fascinating idea, significant obstacles remain. The scientific community continues to question the feasibility of this model, pointing to everything from gravity and expansion to entropy and dark energy. The philosophical and existential implications. After examining the scientific critiques of the black hole universe hypothesis, we're left with questions that extend beyond physics and math. If our universe really does lie within a black hole, the implications touch on deep questions of existence, perception, and the nature of reality itself. In some ways, this theory reshapes our understanding of what it means to exist, as well as our place in a much larger, possibly layered cosmos. If our universe is contained within a black hole, it suggests we are bound by limits we cannot perceive or escape. This challenges the nature of reality, hinting that what we experience might be a slice of a much greater whole, an illusion of space and time created by the structure of the black hole. According to the holographic principle, everything we experience in our three-dimensional world could actually be a projection of information stored on a two-dimensional surface. This would mean that depth, distance, and even time might not be as fundamental as they appear, but are more like the result of data encoded on a distant cosmic boundary. It's a bit like watching a flat movie screen that somehow conveys the illusion of three-dimensional space. We might be living in such a projection, making us part of a reality that's limited and defined by the boundaries of the black hole containing us. This leads to questions about human perception. If we're inside a black hole, our senses and instruments are bound by the cosmic horizon, essentially a limit beyond which we cannot see or measure. In a way, this parallels our own experience of physical and mental boundaries. Just as we can't observe beyond the cosmic horizon, our minds struggle to perceive anything beyond what our senses can process, or what our current understanding of the universe allows. The limits of human perception might reflect the physical limits imposed by our supposed black hole boundary, raising the possibility that everything we know is only a fragment of a much larger structure that we cannot fully access. Thinking about the universe within a black hole also shifts our understanding of existence. If every black hole leads to a new universe, then our universe might just be one bubble in a vast multiverse, with countless other bubble universes existing in black holes across a higher dimensional space. This view would imply that life and existence are not unique to our universe, but may arise repeatedly, with different forms of life developing under different laws of physics in each universe. Our sense of being special would shift, as our universe becomes just one small part of an endless cycle of universe creation. This also connects to the nature of consciousness. If the universe is a projection, then consciousness itself might be an emergent property, something that arises from encoded information. Our awareness, thoughts, and perceptions could be the result of complex information interactions at a cosmic boundary, making consciousness not a separate entity, but something woven into the structure of this universe. This view brings up philosophical debates about free will. If reality itself is encoded and projected, is everything in the universe predetermined by this cosmic encoding, or do we somehow exert independent will within these encoded limits? Could free will exist in a system where the fundamental laws and behaviors are potentially set by information encoded on a boundary we cannot alter? Our understanding of self and scale also changes. Humanity has long perceived itself as the center of existence, but the idea of a black hole universe places us within a cosmic hierarchy, where our universe might be one layer in a complex, nested structure of realities. This changes how we see ourselves, moving us from a central position to being part of a vast, layered system. Recognizing this hierarchy redefines our importance, as we become a part of an intricate cosmos that might be layered with universes created in other black holes, each with its own unique structure and purpose. Living inside a black hole also brings up the intriguing overlap with simulation theory. If the universe is a projection from a two-dimensional surface, it starts to resemble the concept of a simulation, where our reality is a representation of encoded information. Just as a computer program creates an artificial environment that seems real to its inhabitants, our universe might be an elaborate simulation, created by the fundamental laws and encoded data on a black hole's event horizon. This perspective challenges the realness of our experiences, suggesting that what we perceive may be as much a construct as the virtual worlds we can create with our own technology. And if our universe is projected from a black hole, what does that mean for the nature of life and death? If consciousness and physical existence are tied to information within a boundary, then perhaps life and death are simply transitions between different states of information. Consciousness may not end with physical death, but could be part of an ongoing cycle of information that exists in this projected space, altering our perception of mortality. The idea that boundaries could encode all cosmic information hints that life might transcend individual existence, becoming part of a vast network of information that continues beyond what we can currently observe or measure. The concept of interconnectedness grows stronger when we think about cosmic boundaries. If all information about the universe is contained on this boundary, then everything within the universe might be interconnected in ways we can't yet understand. Human consciousness, in this view, may not be an isolated experience, but could be part of a larger universal consciousness, connected across space through the encoded information on a cosmic boundary. If we are indeed within a black hole, what purpose does human life hold? Are we here by random chance, or is there a broader reason for our existence within this cosmic structure? Some might see this as a call to find purpose in exploration, in understanding the universe we're part of and pushing the boundaries of human knowledge. Others might view it as a reason to focus inward, as the cosmic perspective shows us that individual lives are part of a larger system. Purpose might not be inherent, but could be something we create in response to our place in the universe. Time itself becomes a fascinating concept when viewed through this lens. If space and time are projected, then time might be an illusion created by the encoding process on the boundary. Our experience of time flowing forward might be a result of the way information is structured in this universe. This challenges our understanding of time as a linear progression and raises questions about whether past, present, and future are simply constructs within a larger, timeless boundary. Thinking about consciousness in this way also brings up ideas of collective awareness. If all beings in the universe are part of a single projected reality, then each individual consciousness might be a fragment of a larger universal consciousness. In this sense, human awareness could be the universe's way of observing itself, a self-reflective property that allows the cosmos to gain awareness through the conscious experiences of its inhabitants. All knowledge will be constrained by the confines of this cosmic structure, if we are indeed living within a black hole. We may be blind to certain realities because our perceptions are constrained by the projections of this reality. While this doesn't discount the importance of knowing, it does highlight the boundless potential for discovery as we test the limits of our understanding, cognizant that there may be more out there waiting to be discovered. Each of these ideas reshapes our understanding of what it means to be alive, to think, and to exist. It challenges the line between reality and perception, pushing us to consider the possibilities that lie beyond what we can currently measure or observe. In this vast and complex picture, we're left with profound questions about the nature of self, existence, and our place in the cosmos. Future directions and theoretical breakthroughs. As we can see, in the exploration of our potential existence within a black hole, science has offered compelling insights. To test these ideas, we need tools that can observe and measure black holes like never before. Future advancements, both in observational technology and theoretical models, are setting the stage for deeper investigations into these mysteries. The upcoming upgrades to the Event Horizon Telescope, known as the Next Generation EHT or NGEHT, represent a key step forward. This upgrade aims to capture even sharper images of black hole event horizons, allowing us to observe how light behaves in extreme gravitational fields with unprecedented detail. By revealing more about the structure and behavior of black hole boundaries, NGHT could help us understand the nature of the very horizon that might define our universe. In addition to ground-based telescopes, new space observatories like the James Webb Space Telescope, JWST, and the upcoming Lynx X-ray Observatory will let us peer into supermassive black holes at the centers of distant galaxies, examining how these giants formed and evolved in the early universe. If our universe is indeed contained within a black hole, then studying these supermassive black holes might offer clues about how structures like ours could come to be. The European Extremely Large Telescope and the 30-meter telescope will also focus on high-resolution imaging of black holes, providing an even closer look at the intense environments near event horizons. Gravitational wave observatories are another major development. LISA, or the Laser Interferometer Space Antenna, will be a space-based detector designed to capture low-frequency gravitational waves. This observatory could detect waves from massive black hole mergers across vast distances, giving us data on black hole interactions that lie outside the range of current ground-based detectors. As more gravitational wave observatories come online, like the Einstein Telescope and Cosmic Explorer, we'll be able to map black hole events more accurately and observe cosmic-scale mergers, possibly detecting patterns that align with the idea of a black hole universe. Beyond observing black holes directly, we are also venturing into the realm of quantum physics and high-energy experiments to understand the inner workings of black holes. The Large Hadron Collider, LHC, along with its upcoming high-luminosity upgrade, might provide insights into particle interactions at energy scales that mimic black hole environments. For example, some theories suggest that micro-black holes or analogues of black hole event horizons could emerge under the extreme conditions created by the LHC. If this happens, we could observe black hole-like behaviors in the lab and study their properties directly. Future particle accelerators, like the Future Circular Collider, FCC, or a potential muon collider, could push these experiments even further. With these machines, scientists hope to explore interactions at even higher energies, bringing us closer to understanding how matter and gravity behave near black hole thresholds. Experiments using ultra-cold atoms or intense lasers are even creating tabletop black holes, miniaturized environments that mirror certain black hole properties, allowing us to study phenomena like Hawking radiation and quantum entanglement on a small scale. These analog systems could give us new perspectives on the nature of black holes and the boundaries that might define our universe. As we build more sophisticated technology to observe and simulate black holes, artificial intelligence, AI, is becoming an essential part of the process. AI's ability to analyze massive datasets has already proven useful in black hole imaging. It was AI algorithms that helped process the data from the original Event Horizon Telescope to produce the first image of a black hole. Moving forward, AI will play an even larger role. For example, AI-based simulations of black hole mergers can now model these complex processes in real time, revealing the subtle gravitational waves produced by these events, and showing us how space-time distorts and warps during a merger. Machine learning, a subset of AI, also helps with detecting and analyzing gravitational wave signals. Gravitational wave observatories generate enormous amounts of data, but only a tiny fraction of that data actually contains meaningful information. AI is helping sift through this noise to identify signals from black hole mergers and other cosmic events, potentially uncovering fainter signals that were previously overlooked. Some neural networks are even being trained to predict black hole mass and size based on galaxy data, making it easier to estimate black hole properties where direct measurements aren't possible. AI might also help us unravel the black hole information paradox, one of the biggest puzzles in theoretical physics. The paradox revolves around whether or not information that falls into a black hole is preserved or lost forever. By using AI to process quantum information near black holes, researchers hope to gain new insights into how information behaves around these cosmic giants, which could be key to understanding whether information is ultimately lost or somehow encoded on the event horizon. In cosmology, AI has another fascinating role. analyzing the cosmic microwave background, CMB. Machine learning algorithms can detect faint patterns in the CMB, the leftover radiation from the Big Bang. Some of these patterns might reveal connections to primordial black holes or early black hole formation, potentially offering clues that align with the black hole universe hypothesis. Theoretical breakthroughs are also on the horizon. Researchers are developing new simulations of universe formation within black holes, testing models that might explain how a universe could emerge within a black hole singularity. High-performance computing allows scientists to simulate complex black hole environments and test different scenarios, like the expansion of space-time within a black hole or the role of higher dimensional spaces. String theory and loop quantum gravity are two areas that might provide breakthroughs in our understanding of black hole physics. String theory, which proposes that fundamental particles are one-dimensional strings, could help explain black hole singularities, suggesting they might be gateways to other realms. Loop quantum gravity, on the other hand, seeks to unite general relativity and quantum mechanics by proposing a granular nature of space and time. Both theories offer insights into how black holes might behave at their cores, and if validated, they could reveal new layers to the black hole universe hypothesis. Unanswered questions. Even with all the groundbreaking research and incredible theories surrounding black holes, some of the most essential questions about them and the origins of our universe remain unanswered. Could our universe truly be contained within a black hole? If so, what does that mean for our understanding of reality, existence, and everything beyond the boundaries we currently observe? The black hole universe hypothesis invites us to rethink everything we know, but with our present tools and knowledge, we're only scratching the surface. The biggest mystery is what actually happens beyond the event horizon. We have detailed models and theories, but without direct observation, we're left with many unknowns. Is a black hole's singularity a true endpoint? Or is it the doorway to another universe, just like ours? The idea that black holes might be seeds for new universes suggests that what we call a singularity might be where a new realm begins. But without the ability to peer inside a black hole, this remains purely hypothetical. Then there's the question of information preservation, the heart of the black hole information paradox. Hawking's work on black hole radiation suggests that black holes slowly evaporate, but where does the information that falls into them go? If information truly disappears, it could mean our fundamental understanding of quantum mechanics is incomplete. If, however, information is preserved, it could support the holographic principle, implying that everything inside the black hole, including potentially our universe, exists as information encoded on the event horizon. Dark matter and dark energy also remain perplexing, with possible connections to black holes yet to be fully explored. Dark matter seems to cluster around galaxies and interact with black holes, while dark energy drives the universe's expansion. Could these phenomena be influenced by forces outside our universe, linked to a larger cosmic structure? Or are they remnants of black hole dynamics, leftover forces from beyond the event horizon? As a last philosophical consideration, what does it imply if we are actually within a black hole? Does it alter our perception of the cosmos, our purpose in life, and the significance we ascribe to things? Although existential concerns have always plagued humanity, the prospect that our cosmos is part of a vaster cosmic system deepens these contemplations. It suggests that we could be a part of something far larger, something that our understanding of is just scratching the surface of. The future of black hole research promises even more discoveries and, perhaps, answers. I hope you enjoyed the video. If you did, feel free to subscribe to the channel. Thank you.